So we're going to look at position velocity graphs and kind of understanding where the equations come from and applying them with calculus. So let's say we have the following velocity versus time graph. So we have some object that's moving in one direction and it's going 1.5 meters per second. So that's its velocity. If the object starts at 2 meters, how far has it traveled after 8 seconds? We can kind of logically think this one through, right? Or if you're familiar with stoichiometry or just unit conversion, I can think of it as 1/2 meters every second. And it's gone 8 seconds. So we can use that to cancel out the seconds. And I just multiply those two together. I get essentially 1/2 times 8, which is 4. And then I add that to the initial 2 meters it started. I should get 6 meters. So if I logically think that one through and just kind of convert units, it makes sense. We're going to apply it, though, using calculus one of two ways. So the first way is graphically. If we remember before, kind of as we walk through, to go from position to velocity, I take the derivative, okay? To go from velocity to position, I take the antiderivative. Now, if we also remember that the derivative is the slope of the function at any given point, the antiderivative is the area under the curve. So graphically, I can just kind of look at this and say, well, this is just a rectangle whose shape, if I just fill it in real quick here, is 1/2 by 8. And then I add my additional units, right? So the integral or antiderivative doesn't account for some constant I might have started with. So you can think of this as the 2 is the plus c, that constant we started with. So graphically, I can say, well, that's just 1/2 of 8, which is 4, plus the constant I started with, which is 4 plus 2, which is 6 again. So that's how we can look at it graphically. The other method in which we can do is actually by setting up the actual derivative. So in this case, it's bounded, or setting up the integral, sorry. In this case, it's a bounded integral. I'm going from 8 to 0 seconds, and I have 1/2 dt, because I'm looking at it in terms of time. And since there's no variable t here, I just add the variable. This is then going to become 1/2 t, evaluated from 8 and 0, plus c, my constant, which was 2. Right, so in this case, you can think of it as 1/2 t plus 2 is our equation. I'm evaluating it from 8 to 0, which I'm going to, if I plug it in, I get 1/2 of 8, which is 4 again, plus 2, which is going to be 6 again. So all the methods are appropriate. In some cases, though, the equation of the motion isn't going to be as simple enough that we can just unit convert. It's not going to be as straightforward. So oftentimes it's helpful to know how to take the antiderivative or the derivative. We can also graph this now. In terms of a position versus time graph, it would look like this on our graph, right? And I can see that I start here down at 2 meters and I travel at a constant velocity until 8 seconds has passed, and I see that I end at 6 meters. So let's put this into some further context as to why using antiderivatives are so helpful. When I have a motion that's a little bit more complicated or complex, I can use the antiderivative to model that. So let's say I have a velocity that kind of changes over time, and it's unique in how it changes. We can model it with the equation 2t divided by t squared plus 2. Which is modeled in the graph that you see on the left. And what we can do here is we say, like, well, what if I wanted to know how far this object traveled after 8 seconds? It'd be a little harder to just take the area under the curve or even convert with units, right? And for this case, I really do need to know and take the antiderivative or the integral. So I'd set the integral. It's bounded between 8 and 0 seconds. I have to specify that. We can take an unbounded integral, but that would just give me a function. It doesn't really give me a finite value. So if I wanted to know how far is this object going to travel in 8 seconds, I need to bound it between 0 and 8 seconds. And then I have 2t squared plus 2, all in terms of dt. And to solve this integral, we're going to do u substitution. So we're going to say let u equal t squared plus 2. Then du dt is equal to 2t. So dt is equal to du over 2t. Then I can plug it into my integral to substitute. So from 8 to 0, I get 2t over u. And then instead of writing dt, I'm going to write du over 2t. My 2 t's cancel, and I am left with just the integral of 1 over u, right? So from 8 to 0, 1 over u du, which we know is the natural log. Natural log of u evaluated from 8 to 0. I undo the substitution, right? What did we say u was? T squared plus 2, so it's the natural log t squared plus 2, all in terms of 8 and 0. Now I can leave it here and I can actually graph this. This is now the x of t function, which is going to look like this graph right here. So this is position in terms of time. And I can actually evaluate this, right? So I can look at my calculator. I do the natural log. The natural log of essentially 8 squared plus 2 minus the natural log of 0 squared plus 2. And I get that. So this is, again, our position in terms of time, right? So this is our position at 8 seconds. You can think of it like that, right? So then that's going to give me my position at 8 seconds. X of 8 is 3.50 meters. I can use this to figure out position or acceleration of the graph in terms of just using derivatives and integrals.